Greetings, welcome to another video. So this video will talk a bit more about spin loss and look at ways to approach that issue. And I will say this video will be kind of down in the weeds, and we're going to cover a lot of material real quickly. Anyways, to get into this, so this is, where I got into this was through Thane Heins out of Canada and his bitoroidal transformer. And so this is a copy of, I'm pretty sure he has a patent on it. There's, I would say, a lot of nonsense surrounding what Thane has done, and the concept is really quite simple. So here you have, say, an AC power supply and a transformer. There's your primary on a like a toroid or something out to the secondary, and that's a standard setup. Now, when the primary shoots stuff out to the secondary, if you pull off on the secondary a load, then it generates an EMF, goes back to the primary, increases your draw, your amp draw. All right, that's what those do. So now we go to a bitoroidal. See, one toroid, two toroids. So from an AC or a pulse DC source, the primary flows out to the secondary, and then you have another secondary here and the second toroid, and you'll notice that the second toroid is thicker than this first one. So now if you pull off of here, the back EMF has two places to go. You can go back to primary, or it can go to your other secondary coil. And this is the path of lower magnetic reluctance because it's thicker. And likewise, if you pull off of here, it can go to here or here, and it goes back to here for the most part, because again, this is low reluctance, higher reluctance. I built a very crude one of these, I guess years back now, and I'll confirm it does what he mentions, that when you draw off a load, it doesn't change your primary input. And actually, if you draw off, load here, and then you draw off a load here, your output here actually goes up some. And again, the primary, the amp input doesn't change much. It's fairly resistant to what you're doing with the load. Now, there's a number of reasons why I'm kind of excited right now, and we'll get into that at the end of the video. But basically it was like, I don't know if I can make a 10% efficient transformer to begin with, when I was looking at it back then. So, I've gone from like 10 to 12% or something like that. But I'll confirm that does that strange kind of behavior. Now, and perhaps in a subsequent video, I'm planning to redo this now. Again, I'll talk more about that maybe at the end of the video. But the other thing is, what about with when you have a spinning rotor, and this sort of concept applied with a spinning rotor. So if we scroll down, and where is it? Improved power device, and I think this actually is a Canadian patent. I guess it was accepted. I don't know. So you see this. You see this. The embodiment that caught my eye was this one. Okay, so north, south, north, south, north, south. A coil like that, boom, to a coil like that, and a core across the two. And the other reason it caught my eye is, what do you think this is? North, south, north, south. It's actually, 6 poles again as well. Motor, well, here's a motor. So we got everything here except for this. And so all I got to do is do something with that. And he's saying this would work as well, this kind of setup. And what's the idea here is that this is generating, coming past, you put a load on it, and it generates a lens effect which slows the rotor down, puts drag on the motor, amp draw goes up. Same over here. But now, and you don't want electrical connections between these two coils. I almost gave up on that when I put them in series, and it didn't work a couple days ago. But then I remember that's not exactly what I've seen or what he did. That wasn't exactly what I saw with bitoroid. So put these out to separate loads. I'm going to look later on. Maybe you can have them in parallel, but don't put them in series. And have them isolated. So now you generate a lens that opposes the north, but it has a magnetic flux path to go over here. That opposition to the north is now a benefit to the south. The south generates one that's opposing the rotation of the south. It can flow on that same bus line back to there, and you mitigate spin loss. So this is what we're going to do today, is see whether there's anything to that. Now, I learned about this from Thane, but I'll say, and there's a good chance he came up with it all independently. I'll say now that I've been looking at this stuff, there are things that look really familiar. Look at that, and look at that. And now if we go back to what Bedini, look at that. So, I mean, we can start off back here. Here's the Flux Gate transformer, and that's really, you're giving an alternate place for the flux to go. And these are different approaches exactly than what we'll be doing here today. But, here you have this, and I guess you're just spinning this with an iron bar, but it's the same idea. And as he points out, under load, there is no back EMF force on the motor. And then shows it here as well. Magnetic flux gate. Let's skip this. And then here's another one. And this is a motor, G flux gating motor. And so since this is iron, I would guess this is a reluctance motor, as they call it. That you induce a temporary field in the iron and the ferromagnetic material. And then finally we get to something like this. Now, as I said, does that look much like, where is it? Does that look much like that to you? I mean, it's the same thing. Boom, boom. And, where else do you see, this, like Rick Friedrich's machine, where that would be, give me a second. That would be more like this embodiment of it, depending on if he's got these parts thrown in there. But that's also the same idea there. You're just doing another flux path. As I said, I went with this one because all I got to do is throw this part in, and everything else I have right in front of me ready to go. So I said, where was I talking about this? I got this through Thane Heins, but then you see Bedini had done it, and they might have arrived at it independently. And then the bitoroidal transformer, I only spent maybe 10 minutes looking at Tom Bearden's motionless electric generator, but from what I recall, I looked at that and said, oh my gosh, that's the Thane Heins bitoroidal transformer, but it's like on steroids in that, like, he went over every patent, went through all the history. He did a really extensive write-up, but I think it's the same idea. I have to go back and look at it again. Sometimes he's rather hard to follow, but I'm pretty sure the motionless electric generator is going back to the bitoroidal thing. So let's do the Thane thing, and it's going to be important to generate a lot of baseline to see, like, is there actually anything interesting going on or not. And so that's why I'm saying this is a little bit down in the weeds, but let's get moving with it. So I don't have, that was just a little air core. The core should have been bigger, but this is what I have on hand, and we're at 5 volts. And it's got a big air gap now with that coil, even that small coil, because the permanent magnets are so strong. So we'll let that spin up, and that'll be the first part of the baseline. The other thing I'd mention while that's spinning up is Thane has a YouTube channel, and it's, he's only got like 2,500 subscribers. I mean, this is someone who has done interesting stuff, and he's got a lot of videos. I'm embarrassed to say I haven't really watch them all, but this, you know, he's got a lot on this. So I mean, there's plenty of material to go through to make sure that you're doing it right. But I just sort of wanted to give the concepts there, and he's, you know, he's not shy about what he's saying there. So I'm going to have to check this channel out more, but I'm just saying that, you know, it strikes me as a little sad that he only has 2,450 subscribers, and he's got patents on this stuff. And, you know, Bedini might have done it earlier, and I don't know whether that's where he learned it or whether it came up independently, but he's got it patented, at least in Canada. I think those were accepted. All right. So this is a circuit with the Hall effect onto the Arduino, doing bipolar commutation with 2 solid-state relays and pulsing the coil. And there's north-south magnets with 6 poles. And we're running at 5 volts, and we're doing we'll call it 914, and I'll see what the amp draw is. I'll throw it in the spreadsheet. So now we have these 2 coils here, this one, and this one. We're going to run this with these as air cores first, and this one is going out to a bridge rectifier here with cap across it. This one is going out to a bridge rectifier there with cap across it. And we'll just look at the voltages, and then we'll run it with the 1K and 100 ohm load and see what we get just with air cores. So just with no load, you know, it's such a big air gap that it's not able to see much, but we got 1 volt out of there, 1.41 out of the other one. I don't know why. I guess that's a bigger coil. It might also be that the, you know, this is more expensive, so I would guess that one's more accurate, and it's probably this coil is a lot smaller. I didn't measure the inductance, but in any event, they looked about the same, but I guess they're not. So 1 and 1.418. So these being air cores and being so far away, there wasn't much change with the 1K load. 914 and 910 with one of them, down to 908 with 2 of them. So barely changed. The amp draw might have just climbed up a little. I'm going to do it with 100 ohms just to do that. So you work the low resistance 100 ohm load across both the Energizer coils. Again, big air gap, no core. They're just seeing so little flux to begin with that it didn't change things much. I mean, we've only gone down to 903 RPMs. You can make an argument for 37, but it's probably 36 still, starting at 35. But, you know, there wasn't really much to start with. So now, let's again stay conventional, but just throw a core into each of these and repeat what we just did here. So now I've just thrown a few welding rods in there. I mean, it's a tiny core for the size of the coil. And we can see that instead of getting 1 volt out, we're getting 3.1. So it's made a big difference. And now the other one's up to 4 volts. One thing also is you'll see the rotor, this is just freewheeling. I mean, there's no load on the Energizer coils, but the rotor slowed down. 817 versus 914, lost 100 RPMs, even though this is so much higher. So why is that? That's just the cogging from the iron wanting to beat up the magnet. So you got that slowdown. Let me throw that in the spreadsheet. Okay, so the rotor slowed down from 914 to 817, so the amp draw bumped up from 35 to 40, and we're at 4.1 and 3.1 instead of 1.4 and 1. So I think now when we start to load it with a 1K and or 100 ohms, we're going to be able to see the thing start to slow down, probably fairly significantly. I don't know yet, so let's give it a try. So with a 100 ohm load across both the Energizer coils, we've gone from 817 on the RPMs down to 657. And that's what we're getting out across the 100 ohms for each coil. And the amp draw has jumped up to 57 from 40 as it's slowing down there. So now we've got all our baseline. So now we'll have a first go at the Thane thing. Real complicated, huh? Let me just tape that down so it's not rattling. Okay, so we're just freewheeling now. There's just the one welding rod. And one thing, the RPMs are at 752 instead of 817. I don't exactly know why that is. It's possible I bumped something out of place. Because with even less core material, I would think it would be faster. But in any event, that's what I'm seeing right now. 752, so then I drove it to 42. Our voltage is 3.12 out of one of them. No, it's not. It's 2.59. So from 3.12 down to 2.6. And the other one is 2.817. Remember, there's a big difference between the before. You need the coils to be the same size. I should have measured the, I bet that's why it's slowing down too. Maybe. Decent chance. So now there's not as big a difference there. There's just a little difference. But let's load it and see what it does. Okay, so I put 1K across one of them. And so that's now at 1.03. The other one dropped from 2.6 to 2.58. The RPMs are, come on, 750. So RPMs went 752 to 750. Before it went from 817 to 810. So that's good. Now I put 1K across the other coil, and so it went from 2.58 down to 0.99 loaded. This one, 1.0007 RPMs. That's what I'm interested in. 750. 750 with one side loaded, 750 with both sides loaded. So just to kind of highlight the trend here. When we were doing it conventionally with the core, it dropped from 817 down to 793. And here, as we put 1K across each one, here it dropped from 752 to 750 to 750. Even with an air core, it dropped from 914 to 908. So the percentage change, even when you're getting out next to nothing with the air core, is still larger than this 752 to 750. Let's try it with 100 ohms. So with 100 ohm load across both coils, now we drop to 694 RPMs. So we started at 752 and we went down to 694, whereas conventionally we started at 817 and we went down to 657. So isn't that goofy and silly? I mean, we've mitigated spring loss, and just with one of those. Now, as I'm doing this, I'm thinking about why isn't it even better? And I'm pretty darn sure one thing that would improve it is if these coils were matched in terms of induction. And they're not, because when they're separate, you see them doing that. When they're together, they're trying to equalize across there. And that means that the force going back here to help this one, going that way to help that one, is not even. If it was even, I don't think we even would have dropped as much as we did. But there's still one more argument, and maybe we can solve it, is that you started off, just 2.87 and 2.6 versus this and this. And that's because this core is so tiny. So let's see if we can add a little bit more to the core and get it a little bit closer towards there. And if we still see something, then that's really interesting. Okay, before we even get to trying to put in a little bit more core material, what I did instead was I threw maybe another 50 or 100 lines on this. And I still think it's smaller, but you gotta love it when the plane comes together, because now it's just freewheeling. Now 774 freewheeling versus 752. And see what's interesting here is before there was more core material. So if it was magnetic cogging, then there should be less core material, so it should be going faster than 817, but it went all the way down to 752. But then when I added some wire here, now we're at 770, whatever I said it was. So I think it'd be real important to have these balanced. And by balanced, I mean the same inductance. Exact same inductance, or nearly the same in each coil. So to wrap this up, I mean, we can say this does not behave the same as if you just have an iron core and an iron core. And it's silly and goofy, but it's somewhat resistant to spin loss. And we saw that this number went down a lot less. And the other thing I can see that you want to pay attention to is making sure the two coils are the same size, because even without a load, once you have this bridge here, it slowed down when the two coils were different sizes, because I think now it's feeding something over and the other one's the wrong size for it. And when I put a few more lines on that, it got a lot better. Gave it another 22 RPMs. So I think, put an inductance meter on each and get those two matched. But the last thing I'll mention, just in terms of going forward, is I was thinking last night, I wonder, when I was trying to get to sleep, I wonder if they have something like this. So then I looked it up today, and sure enough, they do. Protopasta, I mean, I got to buy from them just for the name. And they have really good reviews. Ferromagnetic iron PLA 3D printer filament, 45% iron, 45% metal. And it's not like $300. So what I'm saying is, you want these cores bigger, and now you can just print the core and do that. You can also wonder about, if you were daisy chaining these, you can wonder about if you have, say, this is the drive coil and that is a pickup coil. And Thane Heins talks about that as well. Okay, so if you made it this far, thanks for coming along. And I hope you enjoyed this. Stay healthy, everyone, and ciao for now. Bye-bye.